Okay, so good afternoon to everyone. This work has been realized at the Mare Center of the University of Milano Bicocca in Fafu, Magudu. The study combines an ecological approach with photogrammetry techniques to provide new insights into the habitat distribution of a common corallivorous organism of the Maldives. Culcita Schmideliana is a corallivorous seastar of the family Orasteridae. It is found in several tropical areas of the Indo-Pacific Ocean up to depth of 50-60 meters. The dimensions of the adult range between 10 and 30 centimeters in some cases, and it is one of the most common echinoderms found in Maldivian reef, although little information is available so far, especially about the factors influencing the distribution of seastars and their habitat selection. An interesting aspect of Culcita is that it has been sometimes used as a model for the study of the well-known corallivorous crown of thorns seastar, Acanthastra planchi, which has focused a lot of attention in the last decades because of its ability to generate large population outbreaks that are catastrophic for coral reefs. Culcita shares some ecological features with Acanthastra. For example, they have the same modality of predation, they have similar spawning period in many areas, and they have similar larval ecology, at least from the duration of the larval stage point of view. The main differences between the two are that Culcita can consume a lower amount of coral prey per year and has a lower fecundity. So it is apparently unable to generate large population outbreaks. Anyway, we found that in the Maldives, it is sometimes possible that Culcita schmideliana population can reach densities that exceed those recorded for Acanthastra planchi in the same area. Like it happened, for example, in what we called an outbreaking event that occurred in Fafu Atoll between 2018 and 2019, as you can see from this table. Moreover, in a previous study always conducted in Fafu Atoll, we found that Culcita schmideliana consume preferentially small coral recruits that are fundamental for reef recovery and reef resilience, selecting mainly two coral genera, namely Pochillopora and Pavona. So you understand that having big populations of these corallivore consuming preferentially small coral recruits of few genera can represent a serious threat for the integrity of the reef environment. So given this information, the goal of the study was to fill the gap of knowledge about the habitat selection of Culcita schmideliana and the factors influencing its distribution, taking into consideration mainly the availability of coral prey and the topographic complexity of sea bottom as possible drivers of Culcita diffusion. To do so, we combined two different approaches, one based on visual census techniques conducted by snorkeling and scuba diving, and one photogrammetry approach that allowed us to digitally reconstruct our study sites. In particular, the investigated area corresponded roughly to the southwest region of Fafu Atoll, where 6 sites were chosen on the basis of logistic necessities. We divided each site into 3 depth ranges, and within each depth range, 3 belt transects were randomly placed to evaluate seastar abundance and density. At this stage, also seastar dimension were noted, and within each transect area, a minimum of 8 photoquadrats was analyzed to evaluate coral recruits density, thus the density of those corals smaller than 10 centimeters in diameter. After this, we performed a standard and we followed a standard photogrammetry workflow that allowed us to build 3-dimensional models of the investigated sites. I don't want to go too much into details now, but if you have any curiosity, please feel free to ask me later. First of all, we took approximately 250 photos per each transect with an overlap of 70–80%. After this, we transferred our photos into a software called Agisoft Metashape, where we have been able to generate a digital elevation model of our investigated sites, like the one you can see here in this image. To evaluate the structural complexity of the reef, we transferred our digital elevation models into a GIS environment in order to analyze model transect of 20 meters. So the first parameter we investigated was the linear rugosity index, defined as the ratio between the three-dimensional profile of a reef divided by the linear length of the transect, as you can see here in this graph. Linear rugosity index is commonly used as an indication of coral reef complexity and is also often correlated to the coral cover. On the basis of our results, we divided our data into three categories, explaining low, medium, and large rugosity of the reef. Another parameter that we investigated was the average slope, which is an indication of reef steepness. The average slope was digitally calculated through algorithms that are often present in GIS environment. And again, we divided our data into three categories, explaining low, medium, and large average slope. Well, coming to our results, a total of 201 seastar was found, meaning an average density of 186.1 seastar per hectare, approximately. The first interesting thing that we found is a sort of confirmation of hypotheses advanced by previous studies that were never tested before, which is that due to its particular body shape, Culcita and Culcita distribution can be influenced by how seastars of different dimensions can move on reef with different topographic features. So to better elucidate this point, you can have a look to these histograms, and you can see that significantly larger specimens were found in areas with the lowest rugosity, possibly meaning that larger specimens were prevented to move on reefs that were more complex and, for example, full of cavities, crevasses, and obstacles, and whatever. Again, we found that significantly larger specimens were found in areas with medium slope value, again, being possibly prevented to climb on reefs that were too steep. In addition to this, we didn't find any significant difference into seastar dimensions in areas with different density of coral prey. To evaluate seastar preference for different habitat categories, we used the van der Ploeg-Scavia selectivity coefficient. So this coefficient allowed us to evaluate the frequency and to compare the frequency of a habitat category in the environment with the frequency of the same habitat category in which seastars were found. The coefficient ranges between +1, meaning exclusive preference, and -1, meaning total avoidance. So you can see from these plots that seastars preferred habitat with average slope, with medium average slope, with a medium value of rugosity, and with a recruit abundance, thus meaning a coral prey abundance in between 10 and 20, and in general more larger than 10. So again, you can see here that seastars refused habitat that were too steep and too complex. Anyway, a selectivity coefficient only gave us a preference for a certain kind of habitat considered alone, without the influence that these categories can have on each other and their interactions. So to define which factors influenced seastar abundance the most, we performed a multiple linear regression analysis that gave us the results that here are displayed as partial regression plots. So basically, this analysis allows you to compare and to evaluate the influence that a variable, or in this case, multiple variable, can have on another variable. So in this case, the influence that average slope, linear rugosity, and coral juvenile density had on seastar abundance. what we found is very interesting because, for example, coral juvenile density didn't even give a significant linear regression equation, meaning that if coral juvenile density has a statistical influence on seastar abundance, this is very little and even negligible. On the other hand, morphological parameters like the average slope and linear rugosity strongly influenced seastar abundance, with linear rugosity being the most influencing factor, as you can see from the level of the R-square value here. So the larger is the R-square value in this analysis, the larger is the influence of the variable on your factor, in this case, seastar abundance. So we can say that reef topographic complexity exerted the larger influence on seastar distribution. So in conclusion, this study provided new information about the distribution and the habitat selection of this important corallivorous organism of Maldivian reef. We confirmed somehow previous hypotheses saying that body anatomy could represent a driver for the habitat choice of the seastar. And despite preferring habitat with a large availability of coral prey and coral recruits, Culcita Schmideliana seemed to select its habitat primarily on the base of the reef topographic complexity that here was expressed as linear rugosity. In summary, these results, we believe that should be taken into account in possible future management programs of the Maldivian coral reefs. Thank you for your attention, and if you have any question, I will be happy to reply. Thank you.